Bhavna, am I audible? Am I audible? We will discuss steady state analysis of AC circuits using Laplace transformation. Discuss steady state analysis. Okay, let us start with steady state analysis of RL circuit using Laplace transformation method. Here you can see RL circuit. Resistor and inductor are connected in series here. Okay, so AC supply of some Vm sin omega t is given to this circuit, and because of this source, the response in this circuit is I of t. So source is V of t and the response is I of t. So because of the source, current I of t is flowing in the circuit. So because of the source, the response in the circuit is I of t. So initially, this inductor will be uncharged. Okay, it acts as open circuit. Now let us apply Kirchhoff's voltage law in this given circuit, and let us see what will be the KVL equation. So here you can see source voltage is Vm sin omega t. So that will be equal to R into I of t plus L inductance L into d by dt of I of t. So that is our KVL equation. So apply KVL Kirchhoff's voltage law to the given circuit. So you will get, applying KVL, Kirchhoff's voltage law, you will get Vm sin omega t equal to R into I of t plus L into di by dt. Consider it as some equation number 1. Now apply Laplace transformation on both sides of this equation. So Vm is constant, you write Vm as it is. So Laplace of sin omega t is omega by s square plus omega square, and R is constant. So write R as it is, and Laplace of I of t is I of s. L is constant. Laplace of di by dt is, yes, I of s plus I0. You can write plus I of 0 plus. You can write that, but here there is no switch, isn't it? There is no switch, so there is no need to consider this initial conditions. So I have not connected any switch. So that's why I have neglected that term here. So simply I have written Laplace of di by dt, di of t by dt as si of s. Okay, so in this you can, in this equation 2, you can take I of s common. What is left over? R plus s. L is left over. So this is our expression for this RL circuit. Now we can further simplify to determine I of s. So our aim is to determine the current response. So I have sent the coefficient of I of s to the other side. So I have got Vm omega by this expression. Now in this expression I have taken L common. So if you take L common, okay, if we take L common, what will happen here? L term is not there. So R by L plus S you will get. Okay. So after taking L common, what I have done is I have sent this L 1 by L to the numerator. So Vm omega by L, okay, divided by S plus R by L. It is, I took L common, but I have written here 1 by L. That's the thing. Something was wrong. That's what I was. This is not 1 by L. This actually I took L common, so I must write here L, not 1 by L. Okay, so I have taken L common, not 1 by L, but I wrote 1 by L there. Okay, take L common, you will get R by L plus S. So send this L to the numerator. So sending L to the numerator means it's in the denominator only, but we are writing in the numerator. So Vm omega by L by S plus R by L S square plus omega square. So this is my expression for current. Now I have to simplify this. So usually if terms are in Laplace, for simplification we usually go for partial fraction method. So I am going for Heaviside partial fraction expansion method. So here I have considered I of s is equal to a by s plus r by l, and since I have two terms in the denominator, isn't it? I have two terms, s plus r by l and s square plus omega square is there. So um, so these two terms, by partial fraction, what you can write it as a by s plus r by l. Here since here square terms are there, that's why I have considered vs plus c by s square plus omega square. Okay, now let us determine a value. Okay, to determine a value, So in the denominator, s plus r by l is there, write it as it is. And in the numerator, write the actual expression in the numerator. So whatever expression was there for I of s, write it in the numerator divided by the denominator of a. At equate denominator to 0. If you equate denominator to 0, so if you equate denominator to 0, s plus r by l equal to 0, s is equal to minus r by l you will get. So s is equal to minus r by l, you just write it. Okay. So now if any term is cancelling, we can cancel it. I think I can cancel these two terms. So what is left over? Vm omega by L by S square plus omega square. Now substitute S value, that is equal to minus R by L. Substitute in this expression. So if you substitute and simplify, you will get Vm omega L by R square plus omega square L square. Okay, Vm omega L whole divided by R square plus omega square L square. That's what you will get. Okay, now cross to determine, we have determined some value for a here. So we have got some expression for a. Give some notation, numbering, some 5. Now we have to determine b value and c value. For that, what I have done is I have cross multiplied equation 4. Where is my equation 4? This one. I have cross multiplied equation 4 and have got this. So if you see, if you cross multiply, what will happen? These denominators will be same. You can cancel the denominators. This is what is left over after cancelling the denominators. And further, what I have done is I have expanded this expression. I have multiplied a with this term, and I have multiplied bs plus c with s plus r by l. Okay. So after multiplication, this is what the expression that I have got. Now compare s square terms. If you compare s square, you see here left side s square is not there, right side s square is there. A s square, b s square is there. That's it. So 0 is equal to a plus b I will get. So a plus b is nothing but equal to 0. Now a plus b equal to 0, b equal to minus a. So b is equal to minus a. Already I have derived some expression for a. So substitute a here, and b is equal to minus of Vm omega L by R square plus omega square L square. Consider it as equation number 6. Now compare s terms in this equation 5. Okay, not equation 5. I didn't give any numbering here. It's okay. So in this I might have given some numbering. It might have been better. So now compare s terms in this expression. S terms, here s is there. Sorry, this s square. So s is there, s is there. Okay. So if you compare s terms, on the left side s terms are not there. So 0 is equal to b into r by l plus c. So b into r by l plus c is equal to 0. So c is equal to minus b r by l. So we already know the expression for b. Substitute b, you will get c. So this is c. Okay, so this is c. Now whatever expression that you have got for c, so I have simply rearranged the terms. Here L is cancelled, so I have cancelled L and I have got this expression. Now substitute this a, b, c in your equation 4. If you substitute, you will get this expression after substituting a, b, c in equation 4. Now after substituting, if you see here, this numerator terms are there. These numerator terms are almost same. Okay, they are same, isn't it? Numerators are almost same. So you can take numerators common. Okay, you can take numerators common. If you take numerators common, okay, and write them aside, okay, or from the numerator you send them aside. So this is next part. So this is it. Numerator I have written it aside. What is left over? 1 by s plus r by l is there, plus numerator I have written aside. Here I might have written minus, but I didn't write. I kept this minus here itself. So numerator term I have written aside. Here what is the coefficient of this? Now s by s square plus omega square, and this numerator also I have written aside. So if you write this numerator aside, you will get the coefficient of it is omega by s square plus omega square. Now consider these terms which were in the earlier, they were in the numerator, those terms as constants. Consider these terms as constant. Now apply inverse Laplace transformation. If you apply inverse Laplace transformation, you will get inverse Laplace of 1 by s plus r by l. You will get e power minus r by l, r by lt. You'll get inverse Laplace of this term. So inverse Laplace of this term, you just determine the inverse Laplace of s divided by s square plus omega square. You will get cos omega t. Okay. Next again determine the inverse Laplace of this term omega by s square. So you will get sin omega t. Okay. So if you know these formulas, you can easily simplify it. Okay. So take the inverse Laplace, you will get the current equation. I of s will become I of t. Okay, so this is the current equation for RL circuit using Laplace transformation. Now let us see a numerical problem for RL circuit. So sinusoidal voltage of 10 sin 100 t is given. So V of t, they didn't give us the circuit diagram. I have drawn this circuit on my own based on the question that is given. So if circuit diagram, sometimes they will give us the circuit diagram in the exam, sometimes they won't give us. If in the question circuit diagram is not mentioned or it is not given, then you have to draw on your own reading the question. So sinusoidal voltage they have mentioned V of t is equal to 10 sin 100 t applied to a series RL circuit. So R and L are connected in series. This is R, this is L, they are connected in series. Resistor of 5 ohms. Resistance value is 5 ohms. And inductance is 10 Henry. Inductance is 10 Henry. Obtain expression for current using Laplace transformation. So we have to determine the current using Laplace transformation. So from the given data, so based on the given data in the question, simply have written some extra terms here. VM. VM is nothing but this is VM 10. And what is this? Sin omega t, isn't it? Omega value is 100. So that's what I have written here. VM and omega value I have written here. Okay, VM and omega value I have written. Now apply KVL. So now apply KVL to this. Apply KVL to this circuit. What do you get? V. What is V? 10 sin 100 t is equal to R into I of t. R is 5 I of t. And L value is 10. So 10 into d by dt of I of t, considered as equation 1. Now apply Laplace transformation to the above expression. So 10 is constant, leave it as this. Sin 100t is what? 100 divided Laplace of sin 100t. Laplace of sin 100t. What do you get? 100 divided by s square plus 100 square, that is equal to 5 into Laplace of I of t is I of s. 10 into 10 into Laplace of d by dt of I of t is s I of s. Okay, same thing which I have discussed earlier in the what to say, in the theory. Okay, in the similar pattern for this numerical problem also I have applied KVL, I have written the equation. Now let us determine the IS. So from this you can take IS common, you will get 5 plus 10s. Okay, so 5 plus 10s, taking I of s common. So what is I of s from this? I of s is equal to, you just send 10s plus 5 to the other side, you will get, where is it here? So 1000 divided by 10s plus 5 into s square plus 100 square. This is what you will get, I of s. Okay. So here I have taken 10 common. This 10 I have taken common in the denominator. If you take 10 common, what do you get? S plus 0.5. Means you have to divide 5 by 10. 5 with 10. S square plus 100 square will remain as it is. So 10, this 10 if you take common, that 10 and this 0 it will cancel, and what is left over? 100 is left over. So I have further simplified it, simply taking the coefficient common, coefficient of S, this S. I have taken this coefficient of S common, and I have further simplified it. I have got an expression here. In the denominator, if you see, S plus 0.5 is there, S square plus 100 square is there. Okay, so I can further, to determine I of S, I can go for partial fractions. Okay, so if I go for partial fractions, have you said partial fraction expansion method? I of S is equal to 100 by S plus 0.5 S square plus 100 square. So you can rewrite it as A divided by S plus 0.5 bs plus c divided by S square plus 100 square. Since it's a numerical problem, no need to derive if you know the expression for A, B and C. If you don't remember the expression for A, B, C, you go for partial fraction derivation. If you know how to simplify an expression with partial fraction, you just solve it. Or later on you determine A value. Since I remember the formulas, I have directly written the formulas here. Formula for A, B and C, and I have substituted all the values that are available. I know Vm value, Vm is 10, omega is 100, and L value is 10 Henry, and R value is 5, so 5 plus omega is 100, L is 10. Okay, substitute, simplify it, you will get A value. Similarly, B, same expression, only minus is there. So, you will get minus of A value. No need to write this expression, or simply write A is equal to minus B or B is equal to minus A and write the expression. And later on, to determine C, formula Vm I know, Vm is 10, omega is 100, R value is 5. Okay, here R is 5, omega again 100, L is 10. So substitute it, simplify it, you will get C value. So after determining A, B, C, substitute that whole A, B, C values in your above equation of I of S. Okay, where is it? Substitute it in your I of S equation. Okay, so if you see here, this 0.009, you just keep it aside. You can write it here. You will get 1 divided by S plus 0.5. And here you I have just split this whole expression into two parts, numerator based on, so I have split the numerator. So 0.009 s divided by S square plus 100 square, I have written 0.0049 by S square plus 100 square. Now, so later on, if you see here, I can keep this 0.0009 and write it here. I can send this also here. So I will get, if I send this to, if I take it common and write it other side, I'll get 1 divided by this. I can go for partial. If I go for inverse Laplace transform, I can replace it with e power minus 0.5t. Similarly, if I send this 0.009, if I take it common and write it aside, I have s divided by S square plus 100 square. Okay, so that also I can replace it with cos omega t. Omega value is 100. And in here, if you see in the numerator 0.0049 is there, in the denominator square terms are there. So if I send this, if I take this common and write it aside, I will get 1 divided by S square plus 100 square. So there is no formula for this. So for that, if there is therefore, in order to simplify it further, what I have done is I have multiplied and divided with 100. So if I multiply and divide with 100, 100 divided by S square plus 100 square is similar to omega by S square plus omega square. So I can, if I go for inverse Laplace transform, I can write sine omega t. Okay, so that's what I have done. So I have further simplified, and later I have gone for inverse Laplace transform. So I have got 0.009 inverse Laplace of this 1 divided by S plus 0.5 is e power minus 0.5, and minus 0.009 into cos omega t, and 4 zeros 49 is into sine omega t. Omega value is 100. Okay. So that's it, simple. If you know Laplace transformation and if you know inverse Laplace transformation, you can easily simplify the circuits and you can easily solve the circuits. So it is in your hands. Okay, so you must have the basic knowledge. If you don't have the basic knowledge, it is of no use. Okay, so let us see steady state analysis of RC circuit. Steady state analysis of RC circuit using Laplace transformation method. Okay, so here R and C, resistor and capacitor, are connected in series. A source is Vm sin omega t, and the response due to the source V of t, response is I of t. Okay, so apply KVL to this above expression. If you apply KVL, you will get Vm sin omega t equal to R into I of t, 1 by C integral of I of t dt. So consider it as equation 1. Now apply Laplace transformation on both sides to the above expression. You will get Vm into Laplace of sin omega t is omega by s square plus omega square. You write R as it is. Laplace of I of t is I of s. 1 by c, you just write it as it is. Laplace of integral of I of t is I of s by s. Okay. So after that, you just take I of s common and you will get I of s into r plus 1 by cs, and you just rearrange the terms to determine I of s. So I of s is equal to, I have got some expression here. In the denominator, I have two terms, s plus 1 by rc and s square plus omega square. Again, I can go for partial fractions to determine I of s value. So I have gone for partial fractions. I have rewritten the above equation as a divided by s plus 1 by rc and bs plus d divided by s square plus omega square. So I might have written bs plus c. I didn't write bs plus c. Why? Because the already c term, capacitance term, is there. Okay, so determine a value, write this whole expression instead of a and write the denominator of a as it is and equate the denominator to 0. You will get s equal to minus 1 by rc, and you further simplify it. You will get a value as minus Vm by omega c whole divided by r square plus 1 by omega c whole square. Consider it as equation number 3. So I need not read out each and every term as it is not at all required. Why? Because if you know the partial fractions, no need to depend on me. Similarly, to determine b and d, simply cross multiply the equation number 2. If you cross multiply, what will happen is the denominators, you will get common denominators on both sides of the equal and you can cancel them. And later on, you just expand that expression. If you expand, you will get this expression. Okay, so Vm omega by Rs is equal to as square plus a omega square, bs square plus bs into 1 by rc, ds plus d 1 by rc you will get. Now after getting this expression, you compare s square terms. If you compare s square terms, here s square is there, here s square is there, only two s square terms are on the left side. There is no s square term. So 0 is equal to a plus b you will get. So a is equal to minus b you will get. Okay, a equal to minus b or b equal to minus a. So I have already determined a value. In here, I have already determined equation 3 is a. So here, since b equal to minus a, minus minus cancel, and what is b? Vm by omega c whole divided by r square plus 1 by omega c square. Consider equation 6. Now compare the constants. Comparing the constants. So next thing that I have done here is I have compared the constants. So where are the constants? This is a constant, sorry. This is a constant and this is a constant. I have compared the constant. On the left side there is no constant. So 0 is equal to a omega square. d 1 by RC. That's what I will get. So A omega square plus d 1 by RC equal to 0. So what is d? Just rearrange the terms, you will get d value. And instead of A, you know the expression for A, substitute A equation, and you will get d. D is equal to Vm omega R by R square plus 1 by omega C square. So now I have determined A, B and D values or expressions. Substitute that in your equation 2. You will get this. And consider these numerator terms common and write them aside after each equation. You just split this equation into two parts. Okay. So if you see here, what I have done specifically is this new denominators, I have written them aside. All the denominators were exactly same, so I took them common. I took the denominators in the numerator common, and I rewrote the expression. And later on I split the whole expression into three parts. Okay, so I can do that once again. I have multiplied. Okay, I can, within this bracket, you can split it into three parts. If you split it into three parts here, this term again, you can write it aside. You write it aside, you will get 1 by s plus 1 by 1 divided by s plus 1 by RC. You will get, take the inverse Laplace to determine I of t, you will get e to the power of minus 1 by RC t. And you split this expression into two terms. If you split it, you will get s divided by s square plus omega square. In another term, you will get Vm omega. Yeah, you have got omega here, you see. Omega by s square plus omega square, you will get. So, inverse Laplace of this is cos sin omega t. Inverse Laplace of this term is cos omega t. Inverse Laplace of this term is e power minus 1 by RCT. So just go for inverse Laplace transformation, okay, and rewrite, you will get this I of t. So whichever term, which what means in the given expression, the terms which are favorable for you to go for inverse Laplace transformations, you just consider only those terms. You consider only those terms and go for inverse Laplace transformation. So this is my current equation. If I go for this means if I go for the numerical problem, I have considered the same circuit. So in this numerical problem, circuit is not given. Only theoretical content is given. So I have to draw the circuit on my own. So here, if you observe, there is a sinusoidal voltage of 20 sin 314t is applied to a series RC circuit. Resistance is given 25 ohms, capacitance is 10 farad. We have to determine the current using Laplace transformation. So if it is specifically mentioned, determine the current in Laplace, you have to determine current in Laplace. So based on the question, I have drawn this circuit. And I wrote some terms from the circuit. Here you can see V of t is 20 sin 314t. 20 is nothing but Vm. 314 is nothing but omega. Okay, R value, C value, they have already given in the question. So that even if you won't write, doesn't matter. Now apply KVL to the above expression. Just apply KVL and write the KVL equation for the given circuit. So apply KVL. After applying KVL, source voltage 20 sine 314 t will be equal to R into I of t plus 1 by c integral of I of t dt. Consider it as equation 1. Now apply Laplace transformation to this above equation. So if you apply Laplace transformation, you will get 20 into Laplace of sine omega t is omega by s square plus omega square. Okay. 25 into I of s, you will get 1 by c. Laplace of integral term is I of s by s, you will get. Consider it as equation number 2. And further simplify this expression. Okay, further simplify this expression to determine I of s. Whichever term you can take it as common, you just take those terms as common. Okay, take those terms as common and determine the I of s. So I have got some expression for I of s. So this is, where is it? This is my expression for I of s, that is I of s is equal to 6280 whole divided by s square plus 314 whole square whole divided by 1 by 10s plus 25. So here I can rewrite this term instead of writing it in the numerator, I can write it here. So if I write it here, so my I of s equation will be somewhat like this. So I of s is equal to 6280 divided by s square plus 314 square into 1 by, here 1 by 10s was there. So what I have done is I have taken 25 by s common. I have taken 25 by s common, and so since I have taken 25 by s common, I have got 25 by s into 1 by 250 plus s I have got. Okay, so this is my I of s equation. Okay. Now what I can do is I can send this 25 by s to the numerator, and I can write s divided by 25. Okay, so simply that's what I have done. In the next slide, you can see I of s is equal to 6280 into s divided by 25 whole divided by 1 by 250 plus s into s square plus 314. Now we can go for partial fraction. We can rewrite this, isn't it? You can rewrite this, and you can write it as s plus 1 by 250. Okay, I didn't write it here, but I might have written like that. Okay, s plus 1 by 250 into s square plus 314 square. I can write. And now I have gone for partial fractions. So if you go for partial fractions, I of s can be written as a divided by s plus 1 by 250 bs plus d whole divided by s square plus 314 square. Okay, consider it as equation number 3. Consider it as equation number 3. So let us determine a value. So a is what? Okay, simply you can go for partial fractions simplification, or simply if you remember the formula for a, write the a formula or substitute all the values. I know Vm is 20, omega is 314, and C is 10 farad, and R value is 25, omega value is 314, C value is 10. Okay, substitute all those values in a, and you will get some value for a. Similarly, we know relation between a and b is equal to minus a, so no need to write formula for b, simply write minus of whatever answer that you have got for a. Similarly, go for d. You remember the formula for d, substitute all the values in that formula, and you will get the d value. Now I have got a, b, d. Now I can determine I of s. I of s is equal to, I have got some 1.0048 whole divided by s plus 1 by 250 plus minus of 1.0048 s plus 785,000 whole divided by s square plus 314. You just divide this, you just rewrite this whole numerator term, you just divide the denominator into two parts. to split the numerator. So you can do that. So I have split it. I have rewritten like this. Okay. So here I can write this term. I can go for inverse Laplace now. I will consider this as constant and into 1 divided by s plus 1 by 250. If I take the inverse Laplace of that, I didn't take the inverse Laplace in this slide. I have not done. I have done some other simplification. So if I go for inverse Laplace, I will get e power minus 1 by 250t. And here I can keep this constant aside, and if you see here, s divided by s square plus 314 square is there. So inverse Laplace of s by s square plus 314 square, I will get cos omega t, that is cos 314t. And if you see here in the numerator, some huge number is there, and the denominator s square plus 314 square is there. So for simplification, what I have done is I have multiplied this. I have multiplied and divided this term with 314, so that it will be. I wanted to write it in terms of omega by s square plus omega square. So that's how I have written here. See here. Here I have written omega by s square plus omega square. So in that form I have written. So inverse Laplace of that I will get sine omega t. So that's it. So after applying inverse Laplace transform, I have got this expression. Okay, so let us see the steady state analysis of RLC circuit using Laplace transformation. So here R, L and C are there connected in series. Okay, they are connected in series. R, L, C are connected in series. So source is there and response is there. So we can apply KVL. So Vm sin omega t equal to R into I plus L into di by dt plus 1 by C integral of I of t dt. Consider it as equation number 1. Now apply Laplace transformation on both sides. If you apply Laplace transformation, you will get Vm into omega by s square plus omega square R into I of s plus L into s I of s 1 by C into s I of s by s. So consider as equation 2. Now you can take I of s common in the above equation and you will get this expression. Okay, after taking I of s common, you will get this expression later. What you can do is you can further simplify it. What I have done is in the numerator I have 1 by s square plus omega square. I have written 1 by s square plus omega square aside, and besides to that what I have got is 1 by s square plus omega square into Vm omega by L by s into Rs by L plus s square plus 1 by L. See, I have got. So here L by S, actually what I have done is I have taken it common from this expression. L by S I have taken it common and I have sent it to the numerator. So in the denominator I have got two terms, s square plus R by Ls plus 1 by Lc term I have got. So now I have considered it as equation 3. So here this in the denominator, this is a quadratic expression. Okay, this is a quadratic expression. For this quadratic expression, you can determine the roots. If I determine the roots and if I compare them, okay, so the terms that are available in the roots are under root of R by 12 square and 1 by LC will be there. So if you compare the terms within the roots. So here I have skipped that. Okay, so for differential equation simplification, if you go through the differential equation simplification, it will be there. Okay, so that you can write it down here, and you just compare the under root terms. If you compare, if r by 12 within that root term square is greater than 1 by LC, then the roots are real and unequal. So this is the plot that you get when roots are response that you get for the current when the roots are real and unequal. A response will be overdamped response. Okay, so since the roots are real and unequal, so s plus a, s plus b, okay, they are real values. A and b are real values and a and b are unequal values. Okay, so you can equate s square plus r by l s plus 1 by lc, this whole term you can equate with this. Okay, so based on the roots that you will get for the condition that you have considered, and you can now for instead of writing this whole term, you just replace it with these two terms and go for partial fractions. Okay, so I have gone for partial fractions. I of s is equal to a by s plus a plus b by s plus b plus cs plus d by s square plus omega square I have written. After that I have gone for inverse Laplace transform. If I go for inverse Laplace transform, this is what I will get. Okay, so I of t is equal to a e power minus at plus b into e power minus bt plus I am sine omega t plus or minus theta. Okay, so now let's another condition. So case 2 is r by 12 whole square less than 1 by LC. Okay, so in that case roots are complex and conjugate, and the response current I of t will be somewhat, the response will look somewhat like this. Okay, so here roots are complex and conjugate, therefore therefore s square plus r by ls plus 1 by lc, you can rewrite it as s plus a whole square plus omega d square. Okay, so this simplification I am not doing it because already before going for Laplace transformation simplification, you must know the differential equation simplification. So in the differential equation simplification, this whole how to simplify, how to determine the roots and all will be available. So you will get this expression from the differential equation simplification. Okay, so consider of this term, you just replace it with this term and rewrite I of s equation. Okay, so after that you can go for partial fractions. So I of s is equal to, where is it, I of s cursor, I of s is equal to as plus b by s square plus omega square plus es plus d by s plus es square plus omega d square, and you can go for inverse Laplace transform. I of t is equal to I am sine omega t plus or minus theta plus I naught e power minus at sine omega t plus or minus theta. So this I have written this whole simplification which I have done here for RLC circuit. If you know how to simplify, okay, how to determine the response for using differential equation method, you can do it for Laplace transformation. So directly some steps I have skipped here. Okay, so because it is already, without knowing differential equation simplification method, you can't go for Laplace transformation simplification method. Okay, so that's why I didn't discuss that. Now next case, I have assumed these two terms are equal to each other, that is r by 2l square is equal to 1 by lc. If they are equal, the roots will be real and equal. So real roots are real and equal, so I have considered s plus a into s plus a or s plus a whole square I have written here. So instead of this term, you can write s plus a whole square. So I of s will be what? By partial fractions, I of s will be this expression. Vm omega s by l s square plus omega square into s plus omega a whole square. So by partial fraction, I will get I of s is equal to a by s plus a, b by s plus a square, cs plus d by s square plus omega square. Now go for inverse Laplace transform, you will get I of t equal to a e power minus at plus bt e power minus at I am sine omega t plus theta you will get. Okay, so this is it. These are the three cases for RLC circuit using Laplace transformation. Okay, so there is a numerical problem. Here I have taken RLC circuit. So R value is 2 ohms, 1 Henry inductance, capacitance is 1 by 2. What did they ask? They have asked us to determine the response, that is I of t. Input is sin t. So applying KVL to the above equation, V of t is sin t. Sin t is equal to 2 I of t, R into I of t plus L into dI by dt plus 1 by C integral of I of t. This is what the expression that you will get. Okay, so after that you just apply Laplace transformation on both sides. So if you apply Laplace transformation, you will get 1 by s square plus 1 equal to 2 into I of s plus s into I of s plus 2 by s into I of s. You will get, you just simplify it further to determine the expression part. Means just rearrange the terms. You will get I of s is equal to 1 by s square plus 1, s plus 2 plus s plus 2 by s you will get. Okay. So here what I have done is further this 1 by s term I have taken it common and I have sent it to the numerator. So my I of s is equal to s divided by s square plus 1 into s square plus 2s plus 2. Okay. So now this whole term can be rewritten using a j operator if you write it in terms of j operator. So if you see here, we already know j square is equal to minus 1. So j square equal to minus 1. So replace 1 with j square. So you will get s square minus j square. So that can represent s plus j, s minus j. Similarly here also you can rewrite like that. Okay, using the j operator. Okay, so here I can write it as s plus 1, s plus s plus instead of 2 I can write minus j, or 2 means coefficient of 2 is 1. So minus j square. I can write minus j square here. Okay, so after that you can go for partial fractions once again. So I have gone for partial fractions. So if I go for partial fractions, then I have to determine the unknown terms. So there are 4 unknown terms here. So yeah, this is A. So you can cancel s plus j and equate s plus j to 0 and simplify. You'll get a value as 1 by 2 into 1 minus j. B, you just s minus j cancel, equate denominator to 0. You will get s equal to minus j and just simplify it. You will get b equal to 1 by 2 into 1 plus j. Okay. And if you want to determine c value, uh, here these terms will be cancelled and equate denominator to 0. You will get s equal to minus 1 minus j and simplify you will get j plus 1 by 2j minus 2. And similarly for d, you can cancel this denominator and this term, substitute s equate denominator to 0. You will get s equal to minus 1 plus j and simplify you will get j minus 1 by 2 into j plus 2. Okay. So just substitute in the I of s expression. Whichever terms cannot be simplified, consider them as constants. And whatever coefficient terms are there for them, you just determine the inverse Laplace. So here in this term, you can see 1 by s plus j is there. Here also you can see 1 by s minus j is there. Here you can see j plus 1, s plus 1 by j, that also can be simplified. Here also j minus 1, s plus 1 minus j, you can simplify. So go for inverse Laplace transform. Okay. So whichever term I have not put in the brackets, those terms you consider as constants. You write them as it is. Inverse Laplace of s plus j, you will get e power minus jt. Inverse Laplace of s minus j, you will get e power jt. Inverse Laplace of j plus 1 by s plus 1 by j, you will get e power minus 1 minus j, sorry, minus common 1 plus jt. And here inverse Laplace of this term, you will get e power minus of 1 minus j. Okay, so this is the simplified expression after going for inverse Laplace transformation. So that's it. This is the steady state analysis using Laplace transformation method. So I will conclude this session. Rejoin the session late after. I will just close now. You just rejoin again.